We are continuing with functions and graphing and a whole bunch of really good advanced ideas that we're seeing in Algebra 1 that we will see again in Algebra 2 and pre-calc. So these are great. In exercises 1 and 2, estimate the intercepts of the function. Intercepts of the graph of the function. So we have two intercepts. We have intercepts are where the line crosses the x-axis. Where it crosses, let's do this. Where it crosses the x-axis, whoa, that didn't work. Where it crosses the x-axis and where it crosses the y-axis. So wherever it crosses is a point, a location. So we have a couple of them. So we look at the x-axis, we see it crosses the x-axis in 3 places. That number will definitely give you a little help on how many. Later on we'll find out of those, and there'll be real zeros and other items. And then we also have y-intercepts. Where does it cross the y-axis? At here. So if we want to know our x-intercepts are going to be -1. What's that? 1, 2, and 3. So -1, 2, and 3. My y-intercepts. Where does the line or the nonlinear, where does the graph cross the y-axis? And it's going to cross it at 6. So estimate the intercepts. That's a good estimation of what those intercepts would be. So we again are looking at this graph and we look to see, and this is a very interesting one and special in a sense because it's going to cross the x and the y-axis at the same location. So my x-intercept is going to be 0, and my y-intercept is going to be 0 also. So that's a fun one in the sense that that's what it looks like. Now here's the other thing that we can do, and I didn't really go into this because it said estimate, so I was estimating. But if we wanted oh, well, yeah, well, we won't, well, we know intercepts. Here's a big idea. Here's something important. We know, and let's get really rudimentary. Let's work with linear lines. When we have these 2 points, we have the y-intercept, where it crosses the y-axis, and we have the x-intercept, where it crosses the x-axis. We know a point. We know one of the values of the coordinates for those locations. We know in our y-intercept our x value is always going to be 0, and in our x-intercept our y value is always going to be 0. So we know one of the 2 values when we want to find intercepts. So if we wanted to find the y-intercept, we could use this equation, y equals x cubed minus 4x squared plus x plus 6. So remember, when we look for the y-intercept, we plug in 0 for x. So we can plug in 0 for these 3 x's, and that would tell me my y value. That would provide me with this. So y equals 0 cubed minus 4 times 0 squared plus 0 plus 6. And that simplifies. 0 cubed is 0. We would have to do 0 squared and 0 plus 6. Let's do y equals 0 minus 0 plus 0 plus 6. So y 6. When x is 0, y is 6. And that's my y-intercept. So that's checks. That's a nice check on finding. Now, here's the other crazy one. Okay, what if I wanted to find the x-intercept? Well, we know when we find the x-intercept, that my y value is 0. So if I wanted to find it, I would have to substitute 0 in for y into this equation, into that equation, and that's a whole lot harder. That is not Algebra 1. But we would go, okay, 0 equals y, what was it, y cubed? X cubed, excuse me, hello. X cubed minus 4x squared plus x, plus x minus 6 plus 6. And then we would have to do some factoring, and that's a bigger, much harder problem. That would be Algebra 2 factoring. And there's a whole number of things that we could do in order to turn that addition and subtraction into multiplication, and then utilize the zero property of multiplication. But we're not going to do that for today. And we could do the same thing for this one. Those are my approximations. If I wanted to find the y-intercept, I can plug 0 in for x. So that's the easier one. Well, I say easier, and I'm about to get absolutely hammered with that comment. But we can see, so y equals the cube root of 4 times 0 is 0 plus 1. Y equals the cube root of 1. And the cube root of 1 is 1. So that would be my y-intercept. When I plug in 0, I get 1. Now that wasn't very obvious. That doesn't look like 0, 1, does it? 0, 1's right here. So that's very interesting. So that is a bad representation of that. Y-intercept shouldn't be 0, it should be 1. I like that. That came out, y-intercept equals 1. Let's do this graph. Let's do this. Yep, this is a video. This will add a little time to it, but that's okay. Let's go to Desmos and enter in that equation. Let me write that equation down. Just y equals the cube root of 4x plus 1. And let's see what Desmos says. Does it look the same? Desmos, y equals, I think we can go here. Do we have functions? There we go. That's the third root of 4x plus 1. Oh yeah, hello. That graph looks completely different. Oh my, that looks way different than what the book provided. That was very misleading. So let's use that. That equation does not look like that in any sorts. Let's do this. So if I had to pick my y-intercept, and let's do this. I should have probably included. Here, let's actually do this. We'll give Desmos a little cred, and let's do that one instead. There. So if we were going to look for the intercepts, come on, the intercept. So the y-intercept, where it crosses the y-axis, we know specifically that the y-intercept is actually 1. And the x-intercept, where does it cross the x-axis, actually looks like a negative value. That's 1, that's half, so maybe negative 0.25. That seems a little bit more reasonable. And then if I wanted to find the x-intercept by plugging in, I'd go 0 equals the cube root of 4x plus 1. And how do we get rid of a cube root? We cube it. So we would cube this. We would get 0 equals 4x plus 1 minus 1 minus 1. Divide by 4, and we get negative 1/4 equals x. So, that did. So those are not, yes, look at that. Now I don't expect you to know how to factor and do all that stuff. However, if they give you a pretty good graph, you could come up with those answers. And I think that that's really what they want from you. They don't want you solving and doing a lot of the stuff. So let's see if this is a true representation of the function that is given. So in exercise 3 and 4, approximate when the function is positive, negative, increasing, or decreasing. Okay, so it is going to be positive from this point on. So that is positive, and this is positive. So we would say that it's going to be positive. So let's do this. Positive when x is greater than, I guess we can say greater than 0, and when x is less than, what's that, 4? Negative 4? Less than negative 4. And it's negative, it's going to be negative when it's in between there. So that's when it's negative. So I would say that it's negative when x is greater than 4 and less than 0. Okay, I think that's, yeah. And when it is 0 and 4, it's neither positive nor negative because it sits at 0, right? It sits on the x-axis. So that's a little bit of a trick question, or if you were wondering why we didn't write equal signs, because when it is equal, it's right on there. It's neither positive nor negative. All right, the next question says, when is it positive, when is it negative, when is it increasing or decreasing? Okay, increasing, oh, let's do this too. Let's do these colors. So positive, let's use this for negative. When is it increasing? So it's going to be increasing at this juncture. How am I going to, oh, let's do this. So notice this graph is increasing after x is greater than negative 2. So increase at x is greater than negative 2, and it is decreasing. I know that doesn't look like it's decreasing, but it is decreasing. It is decreasing in that direction. So we would consider that decreasing when x is less than negative 2. Okay, and then I think it says, then describe the end behavior of the function. So that's fun. What is the end behavior? The end behavior is going to be this area right here. I don't have any more colors, but let's use, so it's going to be in this section. So the end behavior, I wanted that to be. So this is the end behavior, and this is the end behavior. So the end behavior as x goes to infinity, y goes to positive infinity. So the behaviors, let's do this. End behaviors. As x moves to positive infinity, y is going to move to positive infinity. Meaning, as I move to the right on the graph, notice my graph, my arrow, moves towards positive infinity. And vice versa, as x goes to negative infinity, my y value now goes to positive infinity. So as I move negative, notice I'm still going up, so it's going towards positive infinity. It doesn't have to go to the opposite of it. So I like that. As x goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, it's still going up, so it goes to y is positive infinity. So be careful that one. That one's kind of tricky. All right, we like this. Approximate the function when the function is positive. It's never positive. It's never positive. Never positive. Positive. And when is it negative? So positive, never. I don't know if that's not no solution, but positive. When is it negative? When is it negative is going to be all real numbers. Because it doesn't matter how many x's, and every x value is going to give you a negative result. When is it increasing? It is increasing. Also, all real numbers. So it's always increasing. It's always going up. Increase is going to be all real numbers also. When is it decreasing? It's going to be never. It's never decreasing. And then let's talk about the end behavior. So our end behavior, again, so what's it doing as we move along x? What's it doing as we move negative x and positive x? So as x goes to positive infinity, as x goes to positive infinity, it's going to go, that doesn't go to y, positive. As x goes to positive infinity, it goes to 0. Y is going to go closer to 0. So y goes to 0. And as x goes towards negative infinity, it's going to go, y is going to go to negative infinity because it keeps going down. Yeah, I like that. And we see it's actually never going to touch 0 because no exponent, negative 1/2 to no power will ever give you 0. And we can sort of see that. So when we have negative 1/2 to the x, if we have negative 1/2 to the 1, that equals, that's quantity. So that gives me negative 1/2. If we do negative 1/2 to the second, that gives us positive 1/4. As you have negative 1/2 to the third, that's going to give you negative 1/8. So as we get bigger, that's not going to go. It's just going to flip-flop and get smaller and smaller and closer to 0. Sorry. No parentheses. Mr. Mac made a boo-boo. No parentheses. No parentheses. Huh. Let's see that. I want to see that. Yeah, okay. Okay. There is parentheses. See, I wrote S. Technically, when we have negative 0.5, that negative is definitely outside because, sorry, we're on a tangent. The base of that exponent is that, not this. The negative is there, is outside of it. It's not being affected. So it really is this part and then the negative. So you're going to do all that stuff and then the negative. So that's, I was kind of close, but that negative is outside of, so that's going to be negative, that's going to be negative, because it couldn't be flip-flopping because you wouldn't have this graph. It wouldn't be solid. It would go back and forth, back and forth. So that's why I knew I made a mistake. But we're moving towards 0, negative 1/2, negative 1/4, negative 1/8, negative 1/16. We're moving towards 0. So we're getting closer and closer to that 0 line as we get bigger with our x value. We want 1, 2, that's negative 1/2 to the 4th. Now if we move in the other direction, here's the cool thing about exponents. Is if you have the opposite of 1/2, and let's say that's to the 0, that's going to be, no, it's not going to be 0, it's going to be to the 1. Any number to the 0 power is equal to 1. So if we go back to 0, if we go to 0, we notice that it is 1. That point is 0, 1. And then as we continue, if we go in the other direction, if we go negative, here's the cool one. If we did negative 1, that's going to be equal to the reciprocal of that, and that equals negative 2. So if we plug in a negative 1 for x, we should get negative 2. Let's look at the graph. Negative 1 for x gave us negative 2. Negative 1, negative 2. So that's neat. Hopefully you see that. But notice, we're never going to get to 0. So if we increase our negative numbers, if we increase our negative exponents, if we do to the negative 2, well, first we have to get rid of that negative exponent by flipping the fraction, and that changes. And so 2 to the 2nd is 4, so we get negative 4. So when we plug in negative 2 for x, we actually get a bigger negative. We're never going to get to 0. So that's what that problem deals with. I know that was a big time tangent. Sorry. Sketch a graph of a function with the given characteristics. The function is increasing when x is greater than negative 1 and decreasing when x is less than negative 1. Okay, so so let's get a graph out so we can be concrete, so we know what we're talking about. So function is increasing when x is greater than negative 1. So let's do this. I always like this. Let's draw graphs that make sense. Let's make it thin. Let's put a little color in it. Blue. So at negative 1. So my negative 1 is here. So that graph is increasing when x is greater than negative 1. So to the right of this dotted, my graph is going to be increasing. So let's get a little highlighter. So when x is negative 1, greater than, so it would look like that, right? It would be increasing and decreasing when x is less than negative 1. So that would need to be there. Because how we're going, technically, we look at it in this manner. So it's decreasing to that vertex, and then it's increasing after the vertex. So that looks like an absolute value equation. So that would be an example. And that transition, that vertex where it changes from decreasing to increasing, would be at the negative 1. All right, that's not bad. The function is positive when x is less than negative when x is between that, and then positive at x is greater than 1. All right. Let's get a graph. We got a couple places where we're intersecting or changing direction. X is less than negative 3, so that's one of them. Do I still have this? Let's see if it's still alive. Oh. Yes. Let's back it up. All right, so x is -3. 1, 2, 3, that's -3. And then to 1 is doing something different. And then positive when, oh, function is positive. Okay, so that means we're above. Negative between that and positive. So that's going to look like, so positive here. So that graph needs to be up here. And then negative underneath and positive in that. Okay. So where's the middle? That looks like the middle right there. So we can do that, and we can do that. Right? So positive meaning it's above the x-axis. So this is positive. This is positive. So when x is less than -3, it's positive, and positive when x is greater than 1. So that's good. And then it's negative between that. Okay. I think that that's pretty good. Yeah, I'm just looking back at this one. I want to make sure the function is increasing and decreasing. Yeah, I think that's right. I think that's pretty good. I think that worked. Okay, I love this problem. The graph shows the path of a soccer ball you kick. Your friend's soccer ball reaches a maximum height of 4 feet after traveling a horizontal distance of 82 feet and lands 164 feet from where she kicked. Compare the path of your ball to the path of your friend's ball. Compare your path to, okay, so this is my soccer ball. Let's look at this and get some stats. So my soccer ball traveled 40 meters, and it had a height, max height of 2 meters. Okay, so what can we, and then this is my soccer ball and her soccer ball. So her soccer ball reaches a max height of 4 feet. Max, let's put them in the same, max height of 4 feet, and traveled a distance of 82 feet. So notice one's in meters, one's in feet, and we have to convert. So I know that there's approximately 3 feet in each meter, so this is approximately 6 feet. So my soccer ball was higher. I could kick, no, not crayon. I could kick the soccer ball higher. So I win in max height, and then distance. So 40 meters. 40 meters, again, 3 feet in each meter, so that's 120 feet approximately. So, and horizontal, my horizontal distance is 40 meters. Oh, whoops, sorry. And lands from where she kicked it. Wait, what? Horizontal and lands free horizontal. Oh, what? Your friend's soccer ball reaches a maximum height of 4 feet after traveling a horizontal distance of 82. Oh, yeah, because it's halfway there. That's going to be the max. So, this is a little tricky. So it actually, it didn't travel 82 feet. It traveled 164 feet. That's nice because my horizontal distance is going to be, or this is going to be my max, right? Max height is halfway because it travels up and then it travels down. The ball goes up and then down. And so that was a little tricky. So yes, my friend kicks the ball further at 164 feet. All right. Tried to trick me. Tried to trick me in two places. Feet and meters, and then that little piece of information. That is why reading comprehension is so important. We got to be able to understand the problem so we cannot fall into those mistakes. Good luck.